Let's start with our demotivational poster. Unique. Just because you are unique does not mean you are useful. Again, if you like these, you might check out Dilbert by Scott Adams. It's pretty funny. It's definitely an engineer's perspective. So we'll talk about keys, couplings, and seals today, and it won't take us the entire time. The basic idea is that somehow you want to prevent relative motion between a hub and a shaft. Now that hub could carry a gear or a sprocket or a pulley or some other machine element, but you're trying to keep it from moving relative to the shaft moving. Now, so our goal really is to transmit torque, and a key is one way to do that. You've probably dealt with keys in the past, especially if you've fixed a lawnmower or done anything with any small machinery. Keys are very common, and basically it consists of a couple of components. There's the key itself and then the key seat, or you can also call it the keyway. And that's the cutout in both the hub, which is the part that goes around the shaft, and the shaft, so that the key has some space to fit in. Now there are square and rectangular keys, and rectangular keys are used for larger size shafts, larger diameter shafts. So if you go in your book to page 425, you'll see a key size versus shaft diameter table. It's table 11-1, and it tells you what the standard size key is given a range of shafts. So for example, if the shaft is a 6-inch shaft, that falls in the range between 5.5 and 6.5. That's the row just above the solid line. And that's where we're still using a square key rather than rectangular. And in that case, the key itself would measure 1.5 inches wide by 1.5 inches tall. That's the standard key that you use for a 6-inch shaft, or for a anything over 5.5 all the way to and including a 6.5-inch diameter shaft. Now let's move down to the 6.5 to 7.5. So 6.5 is not included in the range. It's anything over 6.5 all the way up to and including 7.5 inches. So let's say we have a 7-inch shaft. In that case, we're going to use a rectangular key, and it would measure 1 3/4 inches wide by 1.5 inches high. So there is a standard. There's also standards for SI. So if you look at the chart off to the right here on page 425 also, you'll see that there's also similarly shaft ranges in millimeters, and it tells you what the rectangular key size should be and what the rectangular key size should be for those shafts. So make sure you bookmark page 425. It definitely deserves a tab because it's all of your standard key sizes. There are also tapered keys, and tapered keys are made to be driven in. So you put the hub onto the shaft, line it up with the keyway in the shaft, and then you can drive the taper key in. Now the problem with this is that when you drive it in, it can be very difficult to get these back out, but you can get a really nice tight fit, because when you try to push a hub onto a shaft with a key already in place, there has to be a little bit of clearance. And the nice thing about a taper key is that you can reduce the clearance a little bit and get a little bit tighter fit with them. So there's a plain taper key, an alternate plain taper key. These aren't required in a whole lot of machinery. There are some where they're required. I've never used it myself. I've never designed for this, just because most of what I've designed has been smaller stuff. But for the sake of assembly, this can be a convenient key form to use. To solve the problem of getting the darn thing out, there's something called a gib head taper key, and you'll see this more frequently on older equipment. I don't really see a lot of designs with this, though they do exist still. And of course the idea here is that the gib taper key or gib head key has a taper on it that can be driven in to interface the hub with the shaft, but then there's a little arm there on the end, okay, a little nub that sticks up that allows you to pry it out. And there's special tools. They're usually sort of curved, and they're basically a curved wedge, and you just drive them in. And I've got a video to show you that process. You don't have to watch the whole thing. I've got a note about exactly what time you should watch in it. But you'll see him drive in this wedge with a hammer to finally get the darn gib head key out. But of course that's a lot easier to get out. A taper key can be practically impossible to get out once it's driven in. There's another way to pin hubs to shafts using a key type thing, and that's a pinhead key. Essentially, the pin key or the pinhead key is just a key that's a round thing. So you basically match drill these most often. You'll put the hub in place, the shaft in place, and just drill to match the two, and then drive, typically a dowel or something like that in it. Now, a dowel may not be the best example because dowels are usually hardened. As a matter of fact, there are certain materials that are common that are used for keys, and this is another page you need to be aware of, maybe even mark. There's some good information on page 426 and 427 about suggested fillet and chamfer dimensions on keys, and there's also Woodruff Key dimensions. You should look through that, but we're not going to do much with it. Woodruff keys are kind of interesting because the number key, or the number that tells you about the key, is standardized so that the numbers actually mean something, and that's worth looking into. We won't use those. We won't talk about sizing. Mainly we're talking about sizing parallel keys. So page 428 is the page I was going for. Table 11-4 has several different common materials that are useful for making keys. Now, when you make a key, one of the reasons it would be a really bad idea in this situation to use a dowel pin is because the dowel pin would probably be harder than the hub and maybe even the shaft. And so if something fails in this assembly, what you really want to fail is the key, because that's usually the cheap part. That's the easy to produce simple component that can be replaced. And so a lot of times when you design a key, you want to design it to fail. In fact, you want it to be sort of the weak link in the chain so that it fails first if there's an overload situation. And so you'll notice that in table, 11-4 on page 428, again, worth a tab in your book, the strength of these various materials is relatively low, and that's intentional. Now, if you think about what's going on, a lot of people get confused because they think the longer the key, the less likely it is for the key to fail. And while that's true, as long as when the key gets longer, it's interfacing with more and more of the hub and shaft, well then, it's still the key that's going to fail first. It just fails at a higher torque. Because as long as the shaft and the hub are the harder or stronger or less likely to yield material than the key, then it's going to be the key that fails first, regardless of how much engagement length there is. Now, obviously, it would fail at a higher level of torque and therefore power. But anyway, so it would probably be a bad idea to use something really hard here. Here's another bad idea. I actually bought two backhoes, not just one, but two. The first one I bought gave out on me, and I was going to fix it, and it was just too much trouble. It wasn't worth the effort and cost of parts to fix it, and so I gave up on it. And this is from the backhoe I gave up on. You can see one of the reasons why I gave up on this thing. There were a lot of things on it that were very jerry-rigged, and I'll give you a zoom-in view of this thing. Basically, the nut in the center that's holding this wheel in place, I guess whoever owned it before me must have had trouble with the nut backing off. And so they decided to do something kind of like this pinhead key, but a really bad way. Normally what you're doing is you've got a shaft and a hub, not something that screws together. Rather, these are typically things that are, they're a hub that slides onto the shaft. Now this is already a threaded nut. I guess they were having trouble with it backing out because they drilled and tapped into the nut and shaft combination and put another screw in there to keep the nut from backing out. Now, to be fair, it's an old piece of equipment. It's older than I am. It was built in the 60s. And, when you're a farmer and you got to get things done and the equipment's old and it doesn't really matter anyway, maybe this is an acceptable solution. But I'm kind of glad that this backhoe broke and wasn't worth repairing, because literally as I would drive, one of the wheels was probably this one on the right-hand side. It would wobble as you drove. And so I guess I could have ended up killing myself on that thing, so it's probably a good thing the engine gave out. I ended up buying another backhoe for less than it would have cost me to fix this one up, so it was a win all the way around. A stronger backhoe and a little bit newer, not much newer, but this kind of equipment, you expect every other time you use it or so for it to break down, you got to fix something, but it's a whole lot better than a wheelbarrow and a shovel. So anyway, that's a pinhead key, and you can do it right or you can do it wrong. One of the problems with the way this was done on that backhoe is that what's being used as the pin is a threaded member, and so that's certainly not going to perform very well. I never thought about it until now. I guess I could have unscrewed that hex bolt to see if there was actually any shoulder on it, because if there was, I guess they could have drilled in deep enough to make some threads and then drilled in to accommodate the diameter of the bolt itself on the shank. That wouldn't be quite so bad, but still, this is kind of iffy, I guess. All right, so Woodruff keys. We will talk about them a bit. I forgot I had them out of order. I may as well go ahead and tell you about the numbering system because it's kind of interesting. Go to page 427, look at table 11-3. You'll see the key numbers as 202, 204, 406, and so forth. The first number, or 2, represent the nominal width of the key, so W, the width. And so a 202 key, for example, at the first row of that table, is a 1/16 inch width key. Now, why is it a 2? Well, it's how many 30-seconds there are in the width. So 2 30-seconds is the same thing as 1/16. So that's a 1/16 key. Go all the way down to the bottom and you see there's a 24/28. The first two numbers, 24, indicate the width in 30 seconds. So 24 30-seconds is 3/4 of an inch, and that's where it comes from. Now the other number, let's go back to the first row, the 02, has to do with the base circle diameter. You can see B, the base circle diameter. Of course, the key is not all of this, right? The key is just a portion of it. But that diameter is an important dimension. And that diameter is encoded in the second number, and I've got to remember how that is. It must be the number of eighths of the base circle. So 02 would be 2/8, which would be a quarter. Let's see if that works. Yeah, 4/8 would be a half. If we go down to the bottom, it would be 28/8. And now I've got to think. 8 and 8, 16, and 8 is 24, so that's 3 inches. That makes sense. And then we'd have a remainder of 4/8, so that's a half. So that works. It's a pretty simple and interesting system for specifying a Woodruff key. So a number 2428 would be a 3 1/4 inch wide key with a 3 1/2 inch base circle. Now, of course, the advantage of Woodruff key comes in assembly. You can take these things and you can actually sit them in a slot. If my hand represents the shaft and this is the top land of the Woodruff key, of course there's the circular part here, you can set it in an angle. And then what will happen when you slide your hub on from the angled side, then the hub straightens it all out and you can get a real nice tight fit. So a Woodruff key is useful. The way you design it actually is very similar to parallel keys, because really what you're interested in is the shear plane, and you're interested in the faces not being smashed. But let me go through parallel keys so that you can see what all that means. We're not going to design any Woodruff keys in this class. So the common key materials are things like 1020 cold drawn. If you need something with a little higher strength, there are other materials, but you usually want these to be very ductile. So you want them to have very long elongation. And the reason for that is it's likely to have overloading, because understand you're transmitting torque between a hub and a shaft. Whether it's from the shaft to the hub or vice versa, you're transmitting torque. And so there's a lot of force on the side of the key. And if the key, if there's some overload, it's beneficial for the key to be able to give just a little bit rather than just snapping. And that's why this ductile requirement is listed here. But of course, as I said before, you always want the key to be made of a weaker material than the hub and the shaft. Now, I believe your author has some equations that we can use if that's not the case, but it's not wise to make it any other way. All right, so if you consider a simple parallel key, what's going to happen is you're going to have force, an offset force couple, on two surfaces, an upper surface and a lower surface of the key, as in this case, the shaft is driving against the hub, I guess. Yeah, shaft is driving hub. So it's trying to push on the lower part of the key, which is the only thing that the shaft can access. And then, of course, there's an equal and opposite reaction from the hub, assuming that it's not increasing in speed. And so that tends to cause a couple that tends to try and rotate the key in its slot. So there's a couple things that can happen. Either, number one, the surface that has the force on it, you can see the distributed force over the bearing area, which is the half of the key, either that is high enough that it causes compression failure of the material, or if you imagine that shear plane at the interface between the shaft and the hub, that shear plane at the middle of the key could also shear. So those are the two failure modes. And actually, I think the equations, you know what, we're talking about it now, let's go find out. I think the equations, I think I've got them in the slides, but I think it's for, yeah, they've got an equation. If you're on page 428, minimum required key length for shear, that's 11-2, and 11-3 is a minimum required key length for compression. So understand we're talking about a compressive failure of the surface, the upper and lower surface on opposite sides. And then finally, shear failure for the length, 11-2, that's talking about failure along the length of the middle of the key. Now, I don't want you to use equation 11.2 or 11.3 because both of them reduce to the same equation as long as the key is the weakest link. And so I don't think it's wise to design when the key is not the weakest link. I suppose there could be some case where that would be desirable, but I can't imagine it. And so what I would rather you use is equation 11-5, which is the proper equation that takes into account both compression and shear failure. And it's all wrapped up into one nice little equation for you, as long as the key is the weak link. Okay, I don't have the equation, so do look in the book. Again, this is worth either committing to memory or putting a tab in. And I wouldn't highlight 11-2 or 11-3 or 11-4. I would highlight 11-5. That's the useful equation for parallel keys. This is the one we'll concentrate on. Now, a spline connection is kind of like keys, but typically splines are not made with multiple keys. They're made as features on the shaft and the hub. And the idea here is that essentially you have multiple keys. At least that's what it's like. Splines can be an extremely strong connection. You can transmit a whole lot of torque between a shaft and a hub with this. And of course the other nice thing about this, if you think about a key, it's only on one part of the shaft, and so it's like the forces are not balanced on either side of the shaft, and that can tend to offset the hub, which is not good. Whereas with splines, they're around the entire 360 degrees of the interface, and so it can more balance the load, which is an advantage. So the general form includes some minor diameter D and some major diameter capital D, the height of the spline, and then the width of the spline as well. I think that's all I've got on splines. Well, there's some information here. Let's look in the book. I didn't copy all of the stuff from the book into the slides, and I did that intentionally. I didn't copy it on purpose because I want you to be familiar with the book. You really, as I go through all of the lecture, should have your book open. You should be going through the pages and finding where all these things are located. Because on exams and when you're working on projects, you need to be able to quickly go and find essentially the recipe that you need for designing whatever machine component it is, or machine element. So make sure you know where everything's located. Now, splines are something that confuse students quite a lot. There's a couple different kinds, but we're going to deal with SAE straight splines. So page 432 is where you'll find information about splines. It's worth putting a tab there. I'm not going to go through a lot of detail here. I have an example problem on this, but know that there are also splines that are so-called involute splines. Now be careful about this because students always get confused between these two. If you notice, spline information begins on page 431, okay, section 11-5. And your author talks about straight-sided splines first, and then on page 432 he transitions and begins to talk about involute splines. And if all you're doing is just hoping you can thumb through the book and find information or equation that solves your problem, you might accidentally try to use information about involute splines when you should be working with straight splines. So notice that page 432 has a transition in type of spline. The spline type changes, and that's important to understand. So anyway, just be aware of that and know that I'll go through more detail of all these equations and the charts and things and how we use them in the context of an example problem. Now, of course, as I said already, splines are really good because they uniformly distribute the forces that are transferring torque. They have to be very accurately machined. They're commonly made very hard because you don't want their profile to change. You don't want them to yield. You want them to be able to take a lot of load. Sometimes they're relatively brittle, but usually the load is so balanced that they're very tough things. There are times when axial motion needs to be allowed. I have a mowing machine. I should have included a picture of it. I'll try to add some pictures when you look at the slides on Brightspace. They should be there. But I've got a mower, and it's got a deck that hangs out over the front. And I really like it because instead of being a zero turn where the deck is mounted in the middle of the mower, this is nice because I've actually got a whole lot of holes in my yard. Of course, grass still grows in those holes, so it's nice to be able to drive up to the hole, basically cantilever the deck out in front of me, not have to drive into the hole, but still be able to mow the grass. I've got a drainage ditch or two, and it's nice to be able to just drive up to those and cut the grass. Well, This deck is something that can be raised and lowered, and it moves at sort of an angle. There's a couple of hydraulic cylinders, because the deck itself probably weighs at least 200, if not 300 or 400 pounds. It's a heavy deck. It's a 72-inch wide deck with big blades. You know, nice system. I really like it. One of the best purchases I think ever made. 27 horsepower, 3-cylinder diesel engine, and I've been really happy with it this season because I fixed some problems that were really annoying and managed to mow with it, and it wouldn't die on me all the time, which was nice. Anyway. So it's got this front deck, and it has to transfer power from the engine, which is actually mounted behind the driver, all the way through to the front of the machine. And the way it does that is through a series of pulleys and shafts and things. It ultimately goes through the differential case. It doesn't involve the front. The front wheels actually drive, and there's a hard axle in the front, or a hard differential case that goes all the way out to the wheels. It doesn't actually interact with the gearing there, but it does have a shaft that rides through that. And then, so there's basically a spline connection coming out the other side going toward the deck. Well, since the deck itself has to move and that point can't move, there's a connection, there's a shaft that goes between that spline and the gearbox that goes to the blades on the deck. And that shaft actually has 2 universal joints on it, which we'll talk about in just a minute, but between those universal joints is also a splined connection, and that spline connection has male splines on one side and female on the other. And the reason for that is that as the deck, if this is the shaft coming out that drives, as the deck comes up and goes down, the length of that shaft, the effective length of the shaft, has to change. And splines are about the only solution for a shaft that transmits power while sliding. It's a really good system. So in some designs, the clearances and so forth are made so that there can be axial motion, basically change in the length of the shaft, so that you can still drive torque through it. If you have a rear-wheel drive pickup, you have this somewhere along the drivetrain, because on a rear-wheel drive pickup, the back wheels need to move up and down, but the transmission stays essentially at the same point in the frame of the vehicle. And so as the wheels move up and down, the distance between the drive point on the rear differential and the output of the transmission actually changes. It shrinks and grows. And so often there are splines somewhere in that drivetrain to allow that action. So there's 2 types. They're straight and involute. Make sure you know which type you need, and make sure you're in the right area of the text when you're going to look for information and equations and so forth. Another way to prevent relative motion between a hub and a shaft is by pinning. And there's a couple different types. There are straight cylindrical pins, and to get these to stay in, you typically want some type of either a screw that holds it in place on either side, maybe a blind hole so it can't get through, which is a bad idea because then how do you get it out, or a nice interference fit of some sort. There's another way to do this. It's with something called a taper pin, and a taper pin, I absolutely abhor taper pins. Number one, you have to have a tool to machine them, a special tool, which is a pain. Number two, the difference in the taper, the difference in size on either end of the taper is so small it's actually difficult to see when you're looking at some of these things. I bought a boiler from Poland of all places, and it's a wood gasification boiler, works real well. I like it. I've had to take the doors off to work on it and change it and things, kind of customize it. And the handle on the door is what you might think of for a regular, wood stove handle, but it is pinned to the shaft that goes in and activates the unlatching mechanism. It's pinned with a doggone taper pin. I hate this thing. Someday, I swear I'm going to drill it out straight and put instead a spring pin in place, because I can never figure out which way I need to drive the taper pin, and they're pretty hard to drive out. They wedge in fairly well. You can imagine with such a shallow taper, this graphic you see in the center is actually exaggerated. And so it's actually really hard to figure out which way to drive the darn thing out. So I've ended up bending a punch, and then finally realized, oh, I'm going the wrong way. I've actually driven it in harder and then tap it on the other side till it finally comes out. So if I ever have to change these, I'm going to drill them out and I'm going to put a spring pin in place. And a spring pin is nice because a spring pin it's something that's actually larger than the hole. It's literally a spring, and as you push it in, it has a taper on either end. As you drive it in, it springs close. So it's got some spring force to hold it in place. And for the application I've got, there's not enough torque on that handle to need anything more. Now, the Achilles heel of a spring pin is it really cannot transmit much torque. Basically, you've got a round piece of sheet metal in there, and if you put enough torque on the hub holding the shaft still, you can pretty easily shear it. So there's advantages and disadvantages to each one of these. And of course, another solution is to simply drill straight through, thread it all, and put it in a threaded fastener. Of course, there the problem is now you got stress concentration in the interface between the hub and the shaft, and you can tend to break the pin a lot easier. So we're not going to worry about many of these. The only one I want you to know how to design is the straight cylindrical pin, and for that it's a very simple equation. Again, you should mark this equation. It's on the next page, page 434. This is equation 1119. So if you know how much torque needs to be transmitted between the hub and the shaft, and you know what material you want to make the pin out of, then this equation will tell you what diameter of pin is required. Now the real practical side of this is that once you calculate that diameter, you might actually be you might be designing so that the pin fails intentionally at that torque so nothing else is damaged. If that's the case, a lot of times you come out with a required diameter from this equation that is some odd number, something that's not commonly available. It would be very expensive to have a custom reamer and custom pins made and so forth. So what's done in the case where you actually want the pin to break at a particular load, what you do instead is you buy something called a shear pin. If you look on McMaster-Carr's website, just look up shear pin, you'll find them. And they're designed to shear at a particular level of load, and that's the better way to go. But then they're interfaced essentially with a standard size that you drill, and then the area that's supposed to fail is necked down a little bit. It's essentially a turned pin is what it really is. But that way it'll fail at the right amount. But you do need to know equation, what was that, 11-19 on page 434. And I don't mean you need to memorize it. On all of my tests you can use open book, open notes, whatever you want to reference. If you really want to waste time, you can look up stuff online, but I don't recommend it. But you need to know where to find things quickly. I purposely set up my tests so that you have to know what you're doing. You can't just learn it on the fly and get a good grade. Another way to, of course, connect a shaft to a hub is with set screws. And a single set screw often is adequate. Now, of course, the problem is the set screw will commonly go and dig into the surface of the shaft, causing material from the shaft to come up and make burrs, which makes it difficult once you back the set screw out, makes it difficult to pull the hub off of the shaft. The solution for this is to design some flats into the shaft. So you want some machined flats in the shaft wherever you're going to have a set screw, and that eliminates this problem. Of course, most cheap equipment, any lawnmower you buy, they're not going to do this because it costs a little bit more. It's one more operation. But most electric motors you buy have a flat on the shaft for this purpose. I guess in the process of making the motor, they realize this is not much more cost, so they may as well add it as a feature. So a lot of times too you can use two set screws, and what that'll tend to do, a set screw will tend to take the hub and offset it in the shaft. Instead of them being concentric, if this is the shaft and this is the hub, instead of them being nice and concentric, the set screw will tend to offset. And so if you have two set screws, you can kind of mitigate that to some extent. It's still offsetting but in a different direction. Really, two set screws are used more for a tighter connection between the hub and the shaft. Now, I suppose if you really wanted to, you could put a set screw on either side 180 degrees opposed to try and prevent the offset. But if you're really trying to prevent offset, you need something besides a set screw. Speaking of which, in more industrial and larger equipment, there's something called a split taper bushing, and you can't see it here very well, but this is a really good design. These things are great. I think there's even a picture in your text of this that's even better than what I have here. Yeah, here we are. Page 437, if you look at it, you'll see a split taper bushing. Let me describe how this works, because this scan's not very good. What you do is you put the machine element on the shaft. Now, there's a lot of clearance between the bore of the machine element, the pulley in this case, and the shaft, and that bore in the pulley is purposely tapered. Not very much, but just a little bit it's tapered. And so then you slide a bushing onto the shaft, and the bushing interfaces, it has a mating taper for the inside of the machine element, or the real hub, but it interfaces between the hub of the machine element and the shaft. Now, sometimes there are keys included both between the bushing and the machine element and between the bushing and the shaft. Oftentimes it's not necessary. What you can't see in this picture that you can see on page 437 is that the bushing has a little split in it. And what happens when that taper goes in, the taper actually clamps down a little bit. It's kind of like a collet on a milling machine, but most of the time you only have a single split in the bushing. I suppose you could get one with multiple splits. I've never seen one. But the bushing, what it does is as you drive it into the machine element, the tapers wedge together and make the bushing get smaller and smaller in size in that tapered area, which really grabs a hold of the shaft and just doesn't let go. Now, one use of keys is so that you get the machine element in the right orientation with the shaft. That is something that's, you know, possible. In the case of a belt, though, that's completely unnecessary, because there's no, you know, unless you're talking about a timing belt, which this is not, this is just V-belts, there's no way to index anything there. Now, another clever part of this design, you'll notice there are three screws, essentially, that hold this thing together. If you notice, there are 6 holes in the face of the bushing, 3 larger and 3 smaller. The 3 larger holes are clearance holes where the screw simply goes through and engages in threads in the machine element in the pulley. You can see that. You can see 2 of them in the pulley's hub. And so what happens then is those screws are what you use to drive the bushing into the machine element and, you know, tie everything together real tight. The problem is you've wedged things together, and taking those screws out does very little to release the assembly. So you take those exact same 3 screws, and the other smaller 3 holes are actually threaded. You thread the screws in and use the screws as a jack screw to push the, in this case, pulley's hub out of the bushing, and then the bushing releases and can slide off the shaft. These are really good components. These are very reliable, high-power components. These are quality things. You won't see this on a lawnmower you buy down at, you know, any of the big box stores. You'll see this on real industrial equipment. There are many other methods to transmit torque: non-circular shafts, taper screws, press fit. You can read it there. Your author has a nice picture I want you to look at on page 436. Figure 1111 talks about polygonal shapes for preventing relative motion between a hub and a shaft. These are typically more expensive because, you know, it's a little more complicated machining. I've never used or designed any of these. We're not going to in this class. Just know that they are available. They're used on some equipment, but they're not common. A lot of times this non-circular shaft design is something that's more of a holdover from the past in, you know, common machinery. I mean, maybe you'd find this on a tractor or something from particular manufacturers. I know that first backhoe I was telling you about a minute ago, I ended up having to take the fuel tank off of it, and the fuel tank had a link or a shaft that ran through it. It was just the steering shaft. And I swear it must have been just a practice in design, because they used every single, well, just about every single method of holding a hub to a shaft that I could think of. They had pins, they had keys, they had several different things. It turned out you needed about 3 or 4 segments in that shaft in order to be able to assemble it with the fuel tank, which is probably half the reason I decided not to put the thing back together. It was such a pain with the way it was designed. But anyway, some engineer was just practicing, I think, when they designed everything through that steering shaft. Molding on a knurled shaft. This is one technique that I used. When I was at Amatrol, I had to redesign a robot once. We used these little motors called Pitman motors, and they were about so long. They had a gearbox on the end, and I'll never forget this little project. It was an interesting design. Most people that study robotics like I do don't actually get to design or redesign a robot, and you know, in the first 4 years of my career, I had the chance, and it was kind of nice. I enjoyed it. I did make it a better robot. It was stronger when it was done. It was cheaper to manufacture. It used updated components. It was cheaper from that reason as well. It was used more powerful motors and things. Along the way, I needed a motor that had a longer shaft in it, and the motors we were buying were actually gear motors. So the motor itself was only, you know, maybe 3-4 inches long, and then it had a gear head on it that was another inch and a half long, something like that. And there was gear reduction in it, so that you get relatively large torque and low speed output from the motor. And so the default configuration that the company had available had a shaft that stuck out maybe, I think the longest one they had was about 1.5 inches, and it was a 1/4 inch diameter shaft. And for my design, for whatever reason, I can't remember now, I needed a longer shaft on it. Well, if you take the gearbox apart, you could see a gear that had basically been molded onto this little 1/4 inch shaft, so a 1/4 inch diameter, maybe 2 inches long total, maybe 3. And so I was looking at this design, and I thought, well, I need a longer shaft. So I called up the company and I said, I'm looking for a motor with a longer shaft, and the salesman was recommending some other motors, and I looked into them, was looking at the specs. They didn't have the length of the shaft on one of their motors, or maybe it was one he recommended and I couldn't find it. And I said, okay, this sounds pretty good because it's got the power and torque requirements I need. Sounds like it's got a good speed output, but how long is the motor shaft? And what I meant was, how long was that shaft segment coming out, because I hadn't seen anything long enough for my application. And the salesman on the other end of the line said, how long is a Chinaman? And I was in the mode of design, and I was not thinking about jokes or anything like that at all. And I thought, how long is a Chinaman? What on earth is he talking about? He's talking about Chinese people's height. Why on earth would he bring this up in this conversation? How is this relevant? Finally, I realized he was making a joke, and he was saying that how long sounds like a Chinese person's name. So I'll never forget that. It was just a kind of funny thing. And it was at that point I realized, okay, these guys don't have what I need, and probably I'm wasting my time. So I thanked him. I knew that he was just kind of playing with me because he didn't have what I needed. He knew it, and I realized it at that moment, I guess. So I hung up the phone with him, and I designed my own shaft, and I made drawings and everything, so that when we would get these motors in, we'd make a shaft, a quarter-inch shaft that was the length I needed from just stock material. And I needed some way of taking that gear off of the original shaft and mounting it to mine. And so what I did instead, they had overmolded, I think, or something. I don't remember exactly how they had done it. And they used splines. I remember now. They had used these little bitty splines, and I didn't have a good way of making those splines. And the gear material is fairly soft, so I used something called knurling. Knurling, if you ever think of a set of not calipers, but micrometers. If you think of a set of micrometers, as you turn the handle, there's some crisscross hatch pattern on it to give you some grip. That is knurling. And you can knurl a shaft pretty easily. When the shaft is on the lathe, you just run a knurling tool against it, and it basically, well, it's kind of like a set screw, right? It causes burrs on the shaft, and they protrude up above the surface, the nominal surface of the diameter. And so I spec'd a shaft, specified a certain knurling pattern on it in a certain area, and that displaced the shaft material enough that we could press the gear back on and transmit plenty of torque through it. So that's another way of transmitting torque, and I'll never forget that how long comment every time I tell that story.